This is problem 16.163. It's on page 362. The large mechanical tongs shown are used to grab and lift a thick 7,500 kilogram steel slab HJ. Knowing that slipping does not occur between the tong grips and the slab at H and J, determine the components of all forces acting on member EFH. And then there's a hint that says, consider the symmetry of the tongs to establish relationships between the components of the force acting at E on EFH and the components of the force acting on D at DGJ. I did something similar to what they're recommending, but a little bit different. The figures in the book, I'll refer you to that figure. It's figure P6.163. So we're given figure P6.163. Like I said, I'll refer you to that. The mass of the object is 7,500 kilograms. It's being picked up. So I went ahead and just calculated the weight as mg, which is 7,500 kilograms times 9.81 meters per second squared. That came out to 73,575 newtons. The weight in this problem ends up being a variable we can use over and over, so it's nice to just represent it as W for a little while. So I started off thinking about this, and I thought, well, let's start with the free body diagram of the top where there's force pulling up. Now, how much force would be required? Well, neglecting the weight of the mechanism, it's just the weight of the slab that has to be pulled up. And of course, the members AB and AC then are under tension, pulling this hook down to hold the hook in static equilibrium. Now, if I work with this right-hand side member, it's a symmetrical thing. If I work with this right-hand side member where we have AC here, the dimensions are 0.9 meters, 1.8 meters, so an odd root 4.05 meter hypotenuse length. So this is our geometry triangle for scaling AC. Now, if we sum forces on the free body diagram in the vertical direction, we know that W acting up minus 2ABY equals 0. What am I saying here? I'm saying, look, the thing's symmetrical. So the vertical component of AC and AB is exactly the same, and I don't really need to worry about it. We'd have a similar opposite triangle over here, so I can use it just as well. Because both AC and AB have components pulling downward. And being symmetrical, you can sum forces in the horizontal direction and prove that these two are equal to one another. Since I have two of them, well, it's the same thing, so it's just 2ABY. Okay? And so from this, W over 2 is equal to ABY. Now, ABY, the vertical component, would be 0.9 over root 4.05. And so now we can calculate AB if we want to. I went ahead and did that. It's equal to AC. Plug in, let's see, well, you got to rearrange things just a little bit. I won't bother with that. Plug in the weight, rearrange with the fractions, and you'll find that AB, which is AC, is equal to about 82,259.4 newtons. We don't really need that. It's just nice to know. Now, I am going to draw two other free body diagrams. The main thing I wanted to point out is that I know the force in AC and AB. We'll deal with that later. Which, by the way, actually, ABY is just W over 2. Let's make a note of that. ABY is just W over 2, isn't it? What is ABX? I just erased the triangle. I shouldn't have done that. Let me draw it back. 0.9, 1.8, root 4.05. Well, if the vertical component is 0.9, well, let's put it this way. This is similar to the triangle formed by AB, ABY, and ABX, isn't it? So the ratio of the sides are the same. So ABY over, or better yet, let's say ABX over ABY is equal to 1.8 over 0.9. It's just a 2-to-1 ratio. So if I know ABY, is just W over 2, then isn't ABX equal to W? We'll use that later. Let's just hang on to that because that'll be useful. The actual magnitude of AB will not matter all that much. As a matter of fact, to save space, let me just make a note up here. It says, let's see, let's put it over here. ABX is W and ABY is W over 2. That's really the value of the free body diagram that I drew from the beginning. Now, we want to know all of the forces acting on a particular member. Let me draw that member. My drawing won't be very good, but hopefully you'll get the idea. Let's see, what does that member look more like? Let me try to do a better job of drawing it than I did on my solution paper. Let's see, we've got a curve at the back side, the jaw, something like this. Comes over at a pretty steep angle like that. Point E is up here. Point, let's see, F is down here. And then there's force here. Now, since this is clamping onto the steel plate, it's pretty obvious the steel plate would have to push back this way, F1H, with a force HX. Also, the plate is going to push down on this point with a value of HY, because gravity's pulling down the plate, the arm is pulling up the plate, so the plate's pulling down the arm. Okay? Since I don't know the directionality of EX, EY, I just drew them up in a sort of a positive sense with the typical XY coordinate system. And up here, or over here, we'll have just a positive direction, FX, FY. Now, this is one free body diagram. I think I could figure out HY. Let's go off and do that. HY, well, if I think about the plate is pulling down with weight W and being pulled up on either side with HY. It's all symmetrical. Whatever the other side is, I don't remember what that point is. It's J, so JY. It's pretty obvious. JY and HY are equal to each other, and they're just W over 2. So that's not too difficult. That's easy, based on a free body diagram of the plate. But how hard is this arm pulling on the plate or pushing on the side? Well, I count 1, 2, 3, 4, 5 unknowns. I've only got 3 equations for this body. That's it, 3 equations. How am I going to solve this? Well, I won't, not with just this free body diagram. Let's draw another free body diagram. Let's draw the arm that connects here at E, okay? Now that arm, again, I will try to do a better job of drawing it than I did in my solution, so that it looks more like what we've got. So something like this, and it comes down like that. And maybe something like that, okay? Where we have point AB, right, or point B right here, being pulled with force AB. Of course, in reality, there's an ABX and ABY force. Now we know AB is pulling this way because we know that that connecting rod AB is under tension. We've already figured that out from the free body diagram with the W. So we know the magnitude of these two in terms of the weight. They're right here. ABX is equal to the weight, ABY is half the weight. Okay, no big deal. Now, this member connects to point E right about there. This is point E, that's point E, they are together. Since I have 2 free body diagrams and I'm going to reuse these forces, I have to have equal and opposite forces. In other words, I'll have a horizontal force EX this way, right, equal and opposite, and a vertical force EY like that. I haven't introduced any new unknowns so far. These are knowns, these are the same unknowns, and I do have another unknown though to deal with. Point G down here connects to the other arm that goes the other way, and I've got to think about this just a little bit, okay? Let's pause on this and think about the member that's the mirror image that's connected to this member. It is true that FY acts up here, and therefore FY acts downward on the mirror image of what I'm dealing with here. It acts downward. So since this whole mechanism is symmetrical, then that means GY must act downward like that. Now here's the confusing part. If I were to draw the other member, I'm going to try to draw it without too much detail so I can erase it If I were to draw the other member, let's see, it's a mirror image, something like this. Okay, not all of it, just this portion down here, the mirror image. On that member, I would have to have opposites, right? I'd have to have, just like I said, I'd have to have Fy this way. I'd have to have Fx this way. Okay? But this is a mirror of this, at least about a vertical axis. Both Fy and Gy point downward. That makes sense. But notice that Gx would be opposite of this. So Gx would actually be in this direction. We have to be careful about that. Because what I want to say is that the magnitude of Gx and Fx are the same, and Gy and Fy are the same. Okay? So let's make a note of that. In fact, let's just put it right here, that this is equal to Fx, and this is equal to Fy. Okay? So if we're consistent, if we were to draw the mirror image, you might want to draw the whole thing. If you draw the mirror image free body diagrams and you are consistent, you'll find that Gx has to point to the right, while Gy has to point downward. Okay? All right, so we know that Hy is W over 2. We can calculate that magnitude. In fact, I'll just go ahead and write it here. I took 73,575, divided by 2, and I got 36,787.5 newtons. That's necessary because Hy is one of the unknowns that we need, right? We need to know the magnitude of that force, so there it is. We just need the magnitude of the other four forces. So notice what we've got. By drawing this free body diagram, I have not added any unknowns because I'm not going to use Gx, I'm going to use Fx. Well, let me not erase it. I guess you could say, yeah, I've added an unknown, but I've also added an equation. So I'm never going to use Gx or Gy. I'm simply going to substitute Fx and Fy, and notice then that this free body diagram adds no unknowns. Now I should have 3 equations, sum of force in the vertical direction, and horizontal direction, and a moment equation for this body, and 3 more for this. So that's 6 equations and 3 unknowns, or pardon me, 5 unknowns. So we're setting pretty good. Seems strange that we have an extra equation, doesn't it? All right, so let me call this free body diagram 1. We'll call this one free body diagram 2, so we can distinguish between the two. And let me start off with free body diagram 1, summing forces in the horizontal direction. Well, let's see. We got Ex, we got Fx minus Hx, and that sum has to be 0. Okay? If we sum forces in the y direction, what do we have? Ey, Fy, and Hy down. So Ey plus Fy minus Hy equals 0. But we know Hy already. As a matter of fact, if we put Hy on the right-hand side, it's just W over 2. So we'll write Ey plus Fy equals W over 2. Okay. So now we've got 2 equations, 2 sum of force equations for body 1 in the vertical and horizontal directions. Now let's sum moments. It doesn't really matter where you sum moments about. There's a bunch of unknowns. Probably don't sum moments about this point because that eliminates something that you already know. I chose to sum moments about point F. You could sum moments about point E. Quite frankly, you could sum moments about H and you'll get the same result. But I took counterclockwise as positive. If I sum moments about F, at least I'll eliminate Fx and Fy. I thought that would be worthwhile. Okay? Now, let's be careful. Hy, something we know. The horizontal distance, some of these distances are hard to figure out. You really need to look at the figure. But Hy acting downward is going to cause a positive moment. So Hy times its moment arm is 0.3 meters. I'm not going to put units in here. All of my forces are in newtons. All of my dimensions are in meters. So I'll be consistent and everything will work out. Hx, on the other hand, pointing back this way, well, it's going to cause a negative moment. So minus Hx multiplied by the vertical distance between F and H, and that is 0.5 meters. But Ey and Ex also cause a moment about F. Ey will cause a positive moment, so I need the horizontal distance between F and E. So plus Ey, that horizontal distance is 1.5 meters. And Ex, I need the vertical distance between F and E. But EX, notice, causes a negative moment about F. So minus EX multiplied by 1.8 meters. That's the height difference between E and X. Anyway, that sum comes out to 0. So there's our first moment equation, at least the moment equation for body 1. Let's do the same thing for body 2. For body 2, if we sum forces in the horizontal direction, what all do we have? Well, let's see, there's ABX, there's minus EX, minus or plus GX, but GX is FX, so plus FX equals 0. But I don't like this ABX. I know what it is. ABX is just W, isn't it? So what this tells me then is that EX, let's see, how do I want to say this? Yeah, let's do it this way. EX minus FX equals 0, or equals W, pardon me. So just taking these two terms to the other side. If we sum forces in the vertical direction, we'll have ABY minus EY minus GY, but GY is FY, so minus FY. Okay? And that sum is equal to 0. Now ABY is W over 2. So let's rewrite this one as well and say that EY plus FY equals W over 2. Okay. Last but not least, we will sum moments on body 2. I chose to sum about point G because I figured that would get rid of 2 unknowns. And then I'd have to take the moment of 2 knowns, the moment of 2 unknowns, the X and EY, and that didn't seem so bad. So I started with EY. EY causes a positive moment. I just need the horizontal distance between G and E. So that's EY times a horizontal distance of a ½ meter. EX also causes a positive moment. I just need the vertical distance between E and G. So that's plus EX times its vertical moment arm, 1.8 meters. So I've got the moment of EX and EY about G. And then I need the moment of ABX and ABY. Now AB, let's see, I went with ABX next. ABX causes a negative moment about G. So I had to write minus ABX multiplied by the moment arm. Now the moment arm from G up to ABX, or really up to point B, I think that is. Let's see. Yeah, up to point B. That's actually, despite my drawing, higher than point E. Point E is down below. And so you have to add up a couple of dimensions, but it comes out to 2.1 meters. ABY about G causes a negative moment as well, so minus ABY multiplied by, well, let's see, ABY will need the horizontal distance between B and G. And that horizontal distance, again, adding some together, I think, if I remember right, is 2.8 meters. This comes out to 0. So now we've got 6 equations and 5 unknowns. Now, it's a bit unwieldy. Well, one more thing. Let's not forget, I'd like to substitute these two. As a matter of fact, I think what I'll do is say EY times a half plus EX times 1.8 equals, let's take these terms to the other side, ABX, but ABX is just W times 2.1. ABY is just W over 2 times 2.8. So this is just W times 2.1 plus 1.4, because half of 2.8 is 1.4. So that's just 3.5. Okay? It's a bit cumbersome to deal with the equations in this form. Let me show you another way to deal with them. Okay? Notice the equations are all set up. They're good to go. I really don't need the free body diagram. I'm going to leave it for a moment. But I want to make a table for you. Let me start over here. I'm going to have several equations. Equations 1, 2, 3, 4, 5, and 6. Okay? look at the camera and make sure you'll be able to see all those. Yeah, they're all on the screen. So those are the equation numbers. The right-hand side of the equations is either going to be 0 or something involving W. I've been consistent with that. So let's start off, and let's note that the unknowns we have are Hx, we have Fy, we have Fx, we have Ey, and we have Ex. All I've done is arrange the variables alphabetically. So from the sum of forces in the x direction from free body diagram 1, what do the coefficients of these look like? Well, here it is. Ex has a coefficient of 1. Ey doesn't appear in the equation. Fx has a coefficient of 1. Fy doesn't appear in the equation. And Hx has a coefficient of -1. The right-hand side of that equation is 0. So all I'm doing is pulling off the coefficients. You can recreate the equation by saying 1 times Ex plus 0 times Ey plus 1 times Fx plus 0 times Fy minus 1 times Hx equals 0. It's really a linear algebra technique, but it's very powerful, very useful. If we sum forces then in the y direction on body 1, this will be equation 2. We'll try to keep things straight, making this a nice table. Okay. Sum forces in the y direction on body 1, that's this equation. We have no Ex's. We have plus 1 Ey. We have no Fx's. We have plus 1 Fy, no Hx's, and the result is W over 2. Let me make the ones look like ones because my dash, in fact, let me change the color of my table separation lines. Let's go with green. That way we can tell the ones and the numbers from the lines that separate all of the elements of the table. And of course, I don't have all the separating lines in there, just enough to keep everything straight and organized. And I can write the one the way that I like. There we go. Should be clear. Now, what about the sum of moments about point F on body 1? Right here. This is a little more involved. We have an Ey factor and an Ex factor. The Ex factor is negative 1.8. Now, when I wrote it down, I thought, you know, I don't really want a negative sign on Ex. You'll see why later. So I just flipped all the signs. Basically, I multiplied through by negative 1. So then Ex would have 1.8 as its factor. Ey would have negative 1.5 as its factor, just multiplied by negative 1. Right? There's no, let's see, no Fx, no Fy. But Hx has a positive 0.5 factor. Remember, I'm flipping all these signs. And the reason I did that is because I decided to take all this to the other side to leave myself with Hy times 0.3, because I already know that Hy is W over 2. So isn't Hy times 0.3, isn't that equal to W over 2 times 0.3? Or in other words, 0.15 times W. So that left me with 0.15 W on the opposite side of the equation to the variables. And that's the reason I flipped all these and pull them to the other side. So in sort of a shorthand, I have represented all of the equations of static equilibrium for body 1 with just the coefficients of those equations. You'll see why this is very powerful in a moment. For body 2, I decided the next equation, equation 4, is the sum of forces in the x direction for body 2. Does it have an Ex? Yes, it does. It's right here. So Ex has a factor of 1. There's no Ey. There is a negative 1 Fx. Nothing for Fy or Hx. The result then is W. How about summing forces in the y direction? What do we end up with? Well, no x components. Summing forces in the y direction for body 2. No x components. But we do have a positive Ey and a positive Fy, no Hx, and we get W over 2. Now notice something at this point. The sum of forces in the y direction for body 1 and the sum of forces for the body 2 in the y direction, these are redundant equations. they have the same coefficients and the same result. So I haven't gained another equation. This equation here and this equation here are in fact identical to one another. They don't present any new information. So in reality, I don't have 6 equations. I've got 5 independent equations. Okay, the last equation that I called equation 6 is the sum of moments about point G on body 2. Now that equation, notice, only has an EX and an EY component. EX has a factor of 1.8. EY has a factor of 1/2. There's nothing else in this equation except for the right-hand side, which is 3.5W. Now, when you solve equations, what you typically do is you either solve for one variable, well, you're trying to solve for one variable, right? So sometimes you'll rearrange to solve for one variable, plug it into another. That's a difficult way to solve things. That's the long way about it. A much better way to do this is to add multiples of equations together. And you can see from here a little clearer, if I were to multiply this equation by a negative number, by -1, I could add it to this equation. So negative of 6 added to equation 3 would eliminate EX. Okay, so adding multiples of equations together, so multiplying by whatever number you like, because you haven't changed the equation. As long as you multiply through the entire thing by a positive or negative number, it's still the same equation. You haven't changed it. And added together can eliminate variables. It can pull variables out of the equation. So it makes the solution strategy a little more straightforward. It makes it a little bit easier to see in this format rather than this, because this looks like a mess. How are you going to manage that? Let me show you my solution strategy by making not a copy of the table, but something where I will deal with only the coefficients. So EY, FX, HX. I feel like I'm missing something. What have I done? FX. Oh, I missed FY. And I really don't need any of these equations anymore because I've got them in tabular format. So let me just erase that one. It's just a workup of this one. Let's see, yeah. And then the right-hand side. And I'll show you what I'm going to do. To generate the first equation here, I am going to call this equation 7, and I'm going to take equation 1 and add to it equation 4. Why would I do that? Well, I noticed that equation 1 and equation 4 have a 1 and a 1 here, but a 1 and -1 here. So if I add those two together, I will eliminate FX from the resultant equation. So EX, there's one EX here and another EX here. That's 2 EXs. That's the factor on the new one. 0 EYs plus 0 EYs is no EYs. 1 FX minus 1 FX is 0 FXs. 0 FYs plus 0 FYs is 0 FYs. Minus 1 HXs plus no HXs is minus 1 HXs. And then 0 plus W is just W. Now, it doesn't look like I've done anything. I took one equation that had 1, 2, 3 unknowns in it. I added it to another equation that had 1, 2 unknowns in it, and I ended up with an equation with 2 unknowns. I haven't solved for one variable. I have an equation that involves 2. What would it look like? This equation would look like this. It would be 2, in fact, let me write it up here. Let me show you what equation 7 looks like. It's 2EX minus HX equals W. And you can get that by simply combining the sum of force equation in the horizontal direction for body 1. Take this equation and, wait a second. That's the Y equation. I've highlighted the wrong one. Here it is. Take this equation that involves 3 unknowns and add it to equation 4, which is the sum of forces in the horizontal direction for body 2. Look, FX will go away. That's exactly what happened. FX went away, and I get 2 EXs minus HX equals the weight W. But I'm going to leave it in this form. Why would I do that? I did that because I noticed that there are 2 other equations I can add together. See this one, equation number 3 and equation number 6, they both have 1.8 here. More importantly, one has a negative EY, the other one has a positive EY. So I thought I could use this equation 3 and equation 6 to eliminate EY and have an equation in EX and HX, which is something I already have. Then I'll have two equations that only involve two unknowns I'll be able to solve for. In other words, I'm going to create equation 8 by taking equation 3 and adding to it 3 times equation 6. So equation 3 is 1.8 EX. I've got to add to that 3 times equation 6. So equation 6, 3 times 1.8, well, let's see, 3 times 1.8, let's just write it that way. Why would I do that? Because negative 1.5 plus 3 times 0.5 is just no EYs, isn't it? Separation there, it's not too clean. In fact, let's go ahead and figure out what this is. 3 times 1.8 plus 1.8 is 4 times 1.8. 4 times 1.8 is just 7.2. But we end up with no EYs once we multiply this by 3. We've got to multiply the whole thing by 3, see? Then what do we have? Well, let's see. We have, we're adding equation 3 for 3 times equation 6. So that means we have a 0.5 HX. So I don't see any FX's or FY's, but I do see 0.5 HX. Then I have to add on the right-hand side 0.15 W, because I need all of 3, right? Plus 3 times 3.5 W. Now again, this is a bit of a mess, but 3 times 3.5 plus 0.15 times W just comes out to 10.65 W. And now look what I've got. I've got equation 7 and equation 8 where I should be able to eliminate HX and get EX by itself. In fact, what I'm going to do now is take equation 7, I won't call it anything, and add to it 2 times equation 8. Because if I multiply equation 8 by 2, I'll get a 1 in the HX position. I'll get a whole HX. And when I add that together, that will eliminate HX. So I've got to multiply everything by 2. So I'll have 2 plus 2 times 7.2. Well, 7.2 times 2 is 14.4. 0, 0, 0. 2 times 0.5 is 1. Negative 1 plus positive 1 is 0. And then I'll have W plus 2 times this. Well, what is 2 times this? Well, let's see. It's 21 point, let's see, 6.5 and 6.5 would be what, 3 W? But W plus 21.3 W is just 22 W. Sorry, 22.3 W. And look at that. What does this equation say? Well, 2 plus 14.4 is 16.4. What does this equation say? It says that 16.4 times EX is equal to 22.3 W. And look at that. EX is just 22.3 over 16.4 times the weight W. This is a much quicker way to go about things rather than getting confused and making a bunch of mistakes with the raw equations themselves. Okay? So let's start a result here. I just showed you how this works. So EX, if you multiply 22.3 over 16.4 times the weight, where the weight is 73.575, not point, but comma 575, 73,575, you will get EX. It comes out to, it's rounded off, about 100,044 newtons. And that's one of the forces that we need. Now things are a lot easier. We have one of our unknowns. We have EX. EX is a known. If we can find an equation where there's just one other unknown, well, we can use any equation we like. We've worked up this equation. What does it say? Well, I just erased it. I shouldn't have erased it. Let me pull it down and work with it. Equation 7 says 2EX minus HX equals W. So, if I want to get HX from this equation, all I have to do is take 2EX minus W. Just solving for HX. Put HX on the other side, put W on the other side, there we go. I know what EX is. Multiply this by 2, it's about 200,000, and subtract the weight. When you do that, you find HX. So I got HX equal to about 126,513 newtons. That's how hard those sides, those grippers on the side, are pushing together to hold on to the plate. Okay, that was nice. What's next? Well, now look at equation 1. We know EX, we know HX, we should be able to find out FX. So let's see, I think, yeah, I don't end up using equations 7 and 8 anymore, so let me erase them. And now let's just start using these equations. So summing forces in the x direction, the only thing I don't know now is Fx. If I solve for it from here, or you can look there and figure it out, Fx would be equal to Hx minus Ex. So I just need to take Hx from Ex. It's going to be negative 26,000 and some odd, okay? So this is just 126, well, no, positive actually. 126,513 minus 100,044 will give me Fx. That number comes out to about 26,469 newtons. Okay? So I've used equation 1. I've probably used equation 1 up. There's not much more I can do with it. What else can I do? Well, now I've got Ex, Hx, and Fx. Look, Hx, Fx, and Ex are all knowns now. Okay? Is there an equation where I could use that knowledge to get one of these y component equations? Well, look at equation 6. Equation 6 is pretty simple. It has Ex and Ey. So it looks like I'll be able to get Ey from this one pretty easily. It says 1.8 Ex plus 1/2 Ey equals 3.5 W. That's what it says, right? In fact, all I've done is just copy the equation from here. That's what this said. Of course, I erased it, but all of this moved to the other side just becomes 3.5 W. Okay? So I can plug in Ex at 100,044 and solve for the unknown Ey. I'll leave it to you to figure out those details. But when I did this, I came up with Ey equal to about 154,867 newtons. And that then allowed me to calculate Fy because, let's see, it looks like equation 5 or equation 2, which are the same thing. If you know Ey, you should be able to figure out Fy. Okay? So basically what it says is Ey, 1 Ey, plus Fy equals W over 2. So Fy, which is the last unknown, is equal to W over 2 minus Ey. W is, of course, 73,575 newtons. Ey, we just figured out, is 154,867 newtons. Put it all together, and we will get Fy. When I did that, I got Fy as about negative 118,080 or so newtons, and that was the last force. So that means I assumed the wrong direction for Fy, but the rest of them in my free body diagram, which I've unfortunately erased, I assumed the correct direction. And notice these are all forces that act on, remember, EF H, which is exactly what they asked for.